So we're going to have two parts of the lecture in the last topic. All right, you can get back to what you haven't finished with task 3. So now let's focus back on the slides on the projector on your screen. Now we're going to talk about geometric property and geometric distance measurement. So it may be a surprise to you that for the spatial data, we actually don't have some geometric property embedded in the data. So as we know, you guys listen up. As we know, in the vector data is defined by points for the point feature and the vertices for the polyline and polygon features, right? But we don't really have the properties such as the area or perimeter. But these properties are very important in many spatial analysis. So we want to measure or calculate the area parameters of these shapes. So in ArcGIS, we can easily do that with a measurement tool or calculate these geometric properties using the attribute table. So these are very simple, but I want you to understand how the distance or area are calculated in different coordinate systems and on different data models, namely the raster and vector data. So if we were working with a projected coordinate system, so very straightforward, the distance between 2 points are the straight line. And the line is calculated based on the two coordinate, the coordinate of these 2 points. Okay? And then in the geographical system, coordinate system, as we mentioned in the very first class lecture in this unit, it's not a straight line, but a arc segment of the great circle. So this distance here is calculated using this equation based on the latitude and longitude of the points on the spherical coordinate system. And now the measurement of length is also different with raster and vector data. So you can imagine it's very simple if we want to get the length of a polyline. It's basically the sum of the lengths for different line segments. And in vector data, it's calculated based on the number of cells and the cell resolution. So if it's a straight line, vertical line, then we can just get the length by multiplying the number of cells and the cell resolution, right? So each cell is 50 meters in this case. And if it's a oblique line or inclined line, so we're going to use the diagonal distance of that cell. So now the cell's length becomes the square root 2 multiplied by the cell resolution. So in this case, that's 50 multiplied by 1.414. This is also useful later on. We'll talk about calculating the shortest path. And it's also using diagonal length before moving to a cell that is diagonal to the existing cell. Now for measuring the perimeter and area, it's also different in vector and raster data. So in vector data, for perimeter is very easy. Basically, again, the sum of all these line segments. And the area is calculated by summing the areas of the trapezoid. So if we have a line segment here, then we basically go to vertical lines to the x-axis and calculate the area of this trapezoid. And now if we sum all these trapezoids together, we see this trapezoid here is a negative value because xi plus 1 minus xi is a negative value in this case. So eventually we'll get just exactly this area here using this equation. Okay? So again, you're not required to calculate this, but understanding how the area and parameter are calculated in different data models are very important. And with raster data, as you can imagine, it's much easier to calculate the volume, the area, but it's a bit trickier to calculate the perimeter. So again, we're using the cell resolution, so we know the length of each cell. And the perimeter equals to the total number of cells multiplied by 4, so that's all the size, right? Minus the shared cell size in the area. So in this case, the total number of cells are 21, and the shared size are 30. So for example, this is 1 shared side, 2, 3, 4, 5, 6, 7, 8, 9. So that's 30 in total. So that's how the perimeter of a raster data is calculated. Now remember the very first JS lecture, you were asked to use the buffer tool. And at that time, you may not have a good understanding what buffer is for. Well, now we're going to revisit the buffer tool and understand how we use it to create or analyze our data. So the buffer is a distance measurement tool for only vector data. And it creates a zone around the feature or set of features with a distance or width specified by the user. If we look at a point feature, the buffer is created around it and represented by a circle, right? Because that's an equal distance from that point. So what if we have a set of point features? Let's say they are the cellular network towers. We want to see whether these towers can cover this entire area. There's no gap between the coverage. So we can create a buffer with the distance of the range for the signal and examine whether it can cover the whole area. Or it could be a buffer for a line feature. So imagine the line is a road network, and we're concerned about the impact of noise from the road. So we want to see what's the area will be affected by the noise. Or it can be a river. We want to set a protective area along the riparian area along the river. And in some cases, we want to assign different buffer, different width for the buffer. So imagine this could be a road network where we have the highway and the local road network. And again, we're concerned about the noise level. Then with highway, the speed limit is higher, and we also have all these big trucks. So the noise impact area may be bigger than the local roads. Okay, so we can assign variable distance for different features. So when we create a buffer for different features, they may have overlap. So we can use the dissolve to combine different buffer areas to get a single coherent buffer zone. Because later on, when we use the buffer shape for overlay analysis, it can be easier for the processing. So you'll see how the dissolved shape is for different feature types, for points, lines, and polygons. In most cases, you'll be working with the data set from a small area. Could be a city or a neighborhood. But think about it, when we deal with data set from a very large scale, for example, the whole country or continent, there's something we need to consider, right? So the distortion on the map. So if we're talking about a large area, then the buffer with the distance is no longer a circle, right? It should be a ellipse. So in this case, if we're creating a 1,000 kilometer buffer, so the red ones are the Euclidean buffer or the planar buffer, and the blue ones are the geodesic buffer. You see how they look differently? Basically because the length measurement in the high latitude is different from the low latitude. And it becomes more extreme if we increase the width of the buffer. And this can create some very interesting misunderstanding. I found this graph from the magazine The Economist back in 2003. So they want to analyze the coverage of North Korea missile systems, short, mid, and long range. And they basically draw a buffer zone with the coverage of different systems. So do you think this makes sense? Or what's wrong with it? Well, apparently American people won't be too concerned because the longest range will only cover part of Alaska, right? So they should be relieved. But in fact, this is the updated graph The Economist published 2 weeks later in the next issue. So they correct their drawing. Well, now it seems a big threat to America, which is the actual case, the real case. So see if we get the buffer wrong in these circumstances, or how big the misunderstanding would be. All right, so that's a very short lecture section about the lens area measurement and the buffering of GIS. So now you will have a few tasks to practice how we create the geometric measurement and how to create a buffer along different feature data.